Okay, so these are the first of the paper 2 questions, so the SP only portion of the paper. Pencil's got a weight of 0.16 newtons. Okay, so let's write that down. What's the mass? Hopefully you know that these two things are connected by the formula W equals mg, where g is 10 newtons per kilogram. So W equals mg, 0.16 equals m times by 10. Okay, so we need to divide both sides by 10. That means that m is going to be 0.016 kilograms. And we know that there's 1,000 grams in a kilogram, so that's just the same as 16 grams. There we go, the answer's B. So you can see here, this is, we've got the pivot there. Okay, this force is trying to make it move anti-clockwise, to rotate anti-clockwise. So this is going to give us the anti-clockwise moment, and then this force here, okay, is trying to rotate it clockwise. So that's going to allow us to calculate the clockwise moment. So we've got the weight of the pencil, calculate the moment of the weight of the pencil about the pivot. So that's asking us for the anti-clockwise moment, and that's just the force times by the perpendicular distance from the pivot, okay, which is 0.16 times by, ooh, that's a bit naughty, isn't it? That's 3.7. So if you work it out on your calculator, you could leave it as 0.592 Newton centimeters, okay, which would be actually a better answer is 0.59 Newton centimeters. Oh dear, excuse me. Because it should be given to two significant figures, because that's how many significant figures the input data is to. Or you could convert it into meters. Okay, and to do that we'd divide by 1,000, obviously. Divide by 100. My bad. It's not millimeters, it's meters. It's centimeters. Sorry. So we divide by 100. Okay, so 5.9 times by 10 to the minus 3 Newton meters, okay, would also be a good answer there. Okay, so now it's asking us to calculate force F, okay, and it tells us that the pencil's horizontal, so that means the pencil's balanced and it's in equilibrium. So that means that we can use the principle of moments, that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Now we just worked out the anti-clockwise moment in the previous part of the question. Now this is why it's a good idea to write it out in full, because for the answer we want to give it to the same number of significant figures. Yeah. But now we're going to use that in a further calculations, and so that we don't get a rounding error, we want to use the full value, which is 0.592 or 5.92 times 10 to the minus 3. And then this is the kind of sneaky bit here. That's going to be equal to the force which we're trying to find, okay, times by 7.4. Now, if this is in Newton centimeters and this is in centimeters, then the centimeters and the centimeters cancel, and you just get it in newtons, right? So that's a little bit of a kind of shortcut for us, okay, rather than doing the whole thing in meters. Although, of course, you can do the whole thing in meters and you will get exactly the same answer. Okay, let's just prove that to ourselves. So what we could have done is the force times by, okay, so we're going to divide this by 100, 0.074, okay, and then this was going to be 5.92 times 10 to the minus 3. Okay, so now the whole thing's in meters, and if you tap that into your calculator, you should see that it gets you exactly the same answer. Okay, so either of those methods is acceptable there. I think my preferred method is to always put it into SI units. Okay, but you do need to be able to handle standard form for that. Okay, so end of question 1.